Okay, so now we've got the Kalan-Samanzik equation. What we're going to do now is we're going to calculate the beta function, beta, and the anomalous dimension gamma to one loop in our 5-4 theory. So let's just set the calculation up. So what does our Lagrangian look like? Well, our Lagrangian will look like 1/2 d mu phi p d mu phi p. So one index down, one index up. I'm telling you, I'm back in Minkowski space-time. So we're going to do this calculation in Minkowski space. The second thing is I'm working with the physical field. So I'm using a normalized perturbation theory. So I'm going to have to include the counter terms. So here's the counter term for wave function and normalization. Good. So there it is. Now, next I should put in a mass term, but as I told you, I'm setting all of the physical masses to 0. So there will be no mass term for this model. The fact that there's no mass term does not mean that there's no mass counter term. We should add a counter term for every operator that is relevant or marginal and consistent with the symmetries of the theory. So even though we have no mass term, we will still have a mass counter term, delta m squared over 2 phi p squared. And then we have the interaction. So the interaction in this case is minus the physical coupling times phi to the 4, and we will have a corresponding counter term minus delta g phi p to the 4. So let's just make a comment. So first of all, GP, this is not a parameter, it's a number, it's known, and we imagine that it was measured. But there are three parameters, three things that are unknown in this model. So delta Z, delta M squared, and delta G, these are the values of the counter terms. These are unknown. So we need to fix these somehow. And as usual, this is always the logic. The counter terms, so the counter terms are determined by our matching conditions, okay? That's always the case. So let's just talk a little bit about the matching conditions that we're going to use because, well, they're slightly different to what we've used in the past. So the first matching condition, it's again phrased in terms of the Fourier transform of the two-point function. We will require that the two-point function as a function of p is equal to I. That's what you would have had before. So the residue is I. We would have had p squared. Now we would have had minus the physical mass squared, or we set the physical mass to 0. So then we'll just have the plus I eta, which just shifts the pole a little bit. Now, what's slightly unusual is we're going to require this at some scale. We're going to say at p squared is equal to minus m squared. Now, this looks rather unusual. So let's discuss it a bit and let's motivate why we have taken this as our normalization condition. Maybe we'll have our discussion in blue. Good. Okay. So first of all, what were we doing before? Before, we actually wanted to calculate some physical observable, like maybe a cross-section or something like that. And if we do calculate a cross-section or something like that, we're actually interested in some physical quantity that we're going to measure in experiment. It could be a cross-section or something else like that. In that case, the renormalization condition that we had told us that we must have a pole at the physical mass squared of the particle, and the residue of that pole must be equal to I. This was related to physical statements. First of all, the statement of what the physical mass of the particle is. And then secondly, the fact that the physical field should create a particle with probability 1. So that's it, the position of the pole and the size of the residue. Here, we're not interested in calculating a physical quantity. We want to get hold of beta and gamma. Beta will tell us how the coupling changes when we move from one scale to another. So we're interested in how the coupling is changing, not its actual value. And gamma is telling us how the strength of the field changes as we move from one scale to another. So again, we're not interested in the value of the field strength, but only how it changes when we move between scales. So beta and gamma tell us how some physical quantities change, not necessarily the values of those physical quantities, the coupling and the field strength itself. These are the kinds of things that Wilson would have been interested in. So that's what we're calculating. So we're asking a very different question. So not surprising that our normalization condition looks a bit different. Now, to convince you that this is a good one, let me tell you why we choose this. So first of all, notice that p squared equal to minus m squared is not kinematically possible. You know, this is the energy squared minus the momentum squared, and that's always positive. In our case, we've said this is negative. So why on earth would we have set this quantity to be negative? Well, let's just write it out. So this is telling us that P0 squared minus P1 squared minus P2 squared minus P3 squared is equal to minus m squared. Now I want to remind you how we get to Euclidean space. So to get to our four-dimensional Euclidean space, what were we doing? We would do a Wick rotation, and that amounted to setting P4 equal to I P0, or, you know, equivalently, P0 was equal to minus I P4. Well, in that case, P0 squared becomes minus P4 squared. This is minus P1 squared minus P2 squared minus P3 squared. Okay. And this should be equal to minus m squared. Okay, so just pulling out a minus sign, we learn that the square of the Euclidean momentum is m squared. So what does this do? This puts us into one of Wilson's shells. Remember, he broke momentum space up to shells? We're sitting in the shell with a radius r equal to m. So that's what we've done. We're sitting inside one of Wilson's shells now. Okay, so that gives us a nice interpretation, or one nice interpretation of this condition. There's something else we can say. Because p squared is equal to minus m squared is not kinematically possible, we're never going to hit a pole of some particle. There's no particle that has a pole there. There's no bound state that has a pole there. So that means we can freely adjust m. So we're going to adjust m a little bit, and we won't hit a singularity. We won't hit a singularity. Remember, we argued that what the two-point function looks like as an analytic function, it's got a cut and it's got some poles. But because we're putting p squared is equal to minus m squared, we're confining ourselves to a region where there's no cut and there's no poles, because there's no physical states sitting here. Remember, the physical states corresponded to poles, or we had this cut when we've got a continuum of states above the two-particle threshold. So here, there's no physical states that are kinematically possible, so we're not going to hit a singularity. So I can freely adjust m, and everything's going to be perfectly well defined. And that's exactly what I want. I want to know that I can freely adjust m, and this is what we gain by taking this renormalization condition. And once again, let me just stress that this is, of course, two conditions. It's telling us that there's a pole at p squared is equal to 0. So we're saying what the position of the pole is. And secondly, it's telling us that the residue of that pole is equal to minus I. So there are two conditions sitting inside this first renormalization condition. So we'll be able to set two of our parameters. To set the last parameter, we're going to use a matching condition that determines the coupling. And it too is a slight change from what you've seen before. It's again written in terms of the Fourier transform of now the 4-point function. And just as we did previously, we want the connected 4-point function and we want the amputated 4-point function, which means we drop the external legs. And we're going to evaluate this at P1, P2, P3, and P4. And this we will set equal to minus 24, that's 4 factorial I, times by the physical coupling. So this is pretty much the condition that we had previously. This is what you would have written down for your second matching condition. Here comes the difference. We're going to require that P1 plus P2 squared is equal to P1 plus P3 squared is equal to P1 plus P4 squared is equal to minus M squared. And why are we doing this? Again, these choices of the momenta does not correspond to any physical state. It's again not kinematically possible to have these momenta. So we know we're not going to be hitting any poles because a particle is taking on its physical values of energy and momentum. So that means, again, we're not going to meet any singularities when we freely adjust our scale M, and that's precisely what we want to guarantee. So that's why we're choosing these renormalization conditions. So what would we do now? Well, we need to take our Lagrangian. So we want to take this Lagrangian sitting over here. We want to work out a set of Feynman rules. Once we've worked out the Feynman rules, we want to calculate, we'll calculate the 2-point and 4-point functions, but you could calculate any two correlation functions, and we're going to calculate them to one loop. We're going to apply the matching condition to determine the unknown counter terms. And once we've finished, we've got the 2-point and the 4-point function completely determined. We can plug them into the Kalansa-Manzik equation, and requiring that the equation for the 2-point function and the 4-point function are both obeyed will allow us to determine beta and gamma. So that's the roadmap of where we're headed. Next, let's write down the Feynman rules and compute the correlators. We'll do that in a moment.